Assalamualaikum. Now we are starting the next lecture, the electronic configuration, right? So how the electrons are arranged. First, what we did in the previous lecture, that every atom contain quantum shells. The quantum shells further contain what? Subshells. And the subshells contain what? Orbitals. In these orbitals, the probability of finding electron is maximum. But the first question, that why the electrons are arranged like this, like why they're not just roaming around, because they're repelling and they try to minimize repulsion. They're trying to be as far as possible from each other, but they need the maximum nuclear attraction. And during this struggle, the electrons are at certain positions where they are at minimum repulsion with each other and maximum attraction with the nucleus. Such places are called orbitals, where we can find the electron. So the first quantum shell. First, let me share the screen. Wait. Yes. Look, the first quantum shell contain one S, the S subshell and the S orbital are same. The S is same, but P is what? P could be Px, Py, and Pz. And then 3s, and then 3px, 3py, 3pz, and then there are how much? Look, 2 electrons, and then 2, and then 6, and then 3s, 3p, and then 3g, like this. Okay. Now, electronic configuration. What is the first rule? Wait a minute. What is the first rule? Electronic configuration. Electronic configuration, right? In the ground state, the one which we are doing right now, this is called ground state. Why it is called ground state? Wait a minute. In the ground state, electronic configuration electron will enter into low energy orbital or shell first. Orbital. We will go for orbital. Low energy orbital first. So electrons are filled in the increasing energy order of orbital. You know, this is called Auber principle. But we don't study this in Cambridge. It is not in CIE. Not this word. Only the name is not in CIE. Name is not. Wait. Name not in CIE, but it is in Edexcel. Right? The name is not in CIE, but look, this whole thing is in Cambridge. Like, you must know that whatever configuration we are doing, it is based on low energy. So therefore, it's called ground state. Low energy, ground state electronic configuration. First electron enter into low energy. Enter into low energy orbital. Right. So how do we know the energies? The next question is how do we know the energies? Look, how do we know the exact order of energies? Now what you are supposed to do? Look, what you will do. Write 1s neatly. I'm trying to write it neatly. Then 2s and then 2p. And now 3s, 3p and what? 3d. Then 4s, 4p, 4d, and 4f. 5s, 5p, 5d, 5f. 6s, 6p, 6d, and 6f. Like you can go like this. Now, what we are supposed to do? I am crossing these diagonally this way. Right? Look diagonally. Now, when I will cross it. Now, first 1s is filled, low energy. And after 1 is, next is what? 2s. And after 2s, the next is what? 2p and 3s. Look, when you cross it diagonally like this, 1s, then 2s, then 2p, 3s, then 3p, 4s, and then 3d, 4p, and 5s. Look, look. First 1s, then 2s, then this, and this, and this. No. I'm going to do it. Wait. 1s. And after 1s, I'm trying to keep the distance so that it same, so that it looks neat, but I'm trying. Not necessary. No, not good. So what I'm doing, keeping like this, yes. And now, yes, good job. A little bit, okay. Not this way. Yes, not that much good. It's not crossing the 3D. It should cross 3D. It's okay, even if it's like this. Look. So, असल में नीट जरा दिखाने की कोशिश कर रही थी जो कि नहीं दिखा. Okay. It's okay. Energy. So the lowest energy orbital is what? 1s. 1s accommodate 2 electron. And now what? Next is what? 2s. And after 2s is what? First 1s, then 2s, and then 2p, 3s. And then 2p. In 2p there are how many orbitals? 3. There are 3p orbitals. These are not good. 1s, and now what? 2s, and then what? 2p, 2px, 2py, 2pz. And after 2p, next is what? 3s. And after 3s, 3p. After 3p, the next is what? 4s. After 4s, the next is what? 3d. And after 3d, the next is what? 4p. dr5, 10 electron. 4p. After 4p, the next is what? After 4p, it's what? 5s. And after 5s, the next is what? 4d. And after 4d, the next is what? 5p and then 6s. Look, we are doing this for up to krypton 36. We don't need it to go for all, right? To do it for all. So look, first 1s is filled, and then 2s, and then 2p, and then 3s, and then 3p. And then after 3p, it's 4s, not 3d. Now your first question. Like why after 4 is the 3D? Like why 4 is coming before 3D? Look, if we look at this, can you tell me? The space is more at this area. The space is more, the orbitals are less. They are far, far, far. Huh? This is one, and these are just 3. The space is more, the orbitals are less. But as we go away, look, in the 4, this is 4s. I need to change the color. This is 4s, this is 4p, this is 4d, this is 4f, this is 5s, 5p, 5d, 5f. Look, space less, orbitals more. So they repel and they try to be as far as possible is the result. If you look, wait, I hope I'm sharing the screen. Let me check. No, I'm not sharing. Look, the space is less and there are too many orbitals, like they are going in the order 1s and 2s and 2p. And when they reach to this place, there is no order. It's actually the energy, the repulsion. They're trying to be as far as possible, and during this struggle, and even they're very close, they forget about their quantum shell, that okay, I am a 4, so I can't come before 5. No, they like the 5 could be coming in the area of the 4, the 4 could be coming in the area of the 3, like doesn't matter. The thing that matters is what? To have minimum repulsion and to be closer to the nucleus. So these are electrons. They decide their own repulsive and attractive forces. We are not the one who will give them a rule that they are supposed to obey. No, they're not going to obey us. We are just exploring how they are. And when we explored, the conclusion was this. And it is like, this is a way that help you to memorize this. Like, actually, The atom was not given this rule that, okay, go and it was not asked like this way that these are the electron and arrange yourself like this, yourself in this order. Do you understand what I'm telling to you? इनको नहीं कहा था कि ऐसा करो. They were not asked to obey this. They did it, and we are finding methods that help us to understand and to memorize and to have a good, a clear concept, imagination about atoms, that how they could be. But like, what is the main principle behind all these things? The electrons are trying to be what? At minimum repulsion with each other, in which they forget about that, okay, these are the boundaries of 4 and 5 is coming in between, these are the boundaries of 3 and the 4 is coming in between. Like, it's okay. Now, if the electrons are comfortable with their minimum repulsion and more close to the nucleus, we are also okay. We don't have any issue. Do you understand? So the region is less and they get overlapped. You can say they come up and down, and they find their comfort area where they are at low energy. So it's not necessary that after 3p it's exactly 3d that will come. So it can 4s, that can also come. Right? Now, next thing. If I apply this filling on an element, how actually it happens? It happens this way. Wait a minute. I'm using this. Suppose, look, it's chlorine, right? It's what? Chlorine, 17. It has how many electrons? It has how many electrons? 70. So the first electron will go to 1s, low energy. Now its second electron can go to the upper level, but that would be at high energy. So what it will do? It will not go, the second will not go to this. It will pair up because there is place. There is space. It can be placed here. Look, the first electron is here. The second electron can go in 2s if it is empty, but it will not go to 2s. It will pair up with the first, although like this electron knows that it will repel me, but it is still not going too high. It will prefer the repulsion. It will change its spin, and they would be in this, right? So the second one, instead of going to 2s or 2p, it will pair up with anti-clockwise spin. The third one has no place in this, so third one will definitely go to 2s, right? And the fourth one can go up, but do you think the fourth will go at high energy or it will pair up with anti-clockwise spin at low energy? Definitely. So the fourth, now fifth. What the fifth will do? Fifth will go to this. And now what about the sixth? Would it pair up? Not at all. Why? Because there is this place at the same energy. The third will be single. The fourth, no, it's not the third. 1, 2, 3, 4, fifth. The sixth is single. The seventh is also single. The eighth will pair up instead of going to high. The ninth pair up. The 10th pair up. The 11th go to high. The 12th pair up. The 15th, the 16th, the 17th. Single, single, single. Because place is available. And then this is 16, and then this is what? 17. So how? 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So how you will write? 1s2, 2s2, 2p6, 3s2, and 3p5. 1s2, 2s2, 2p6, 3s2, 3p5. Next thing, if you look, in the first shell, 2 electron. In the second quantum shell, 8 electron. In the third quantum shell, 7 electron. So 2, 8, 7. Right? Next, shorthand, shorthand, sorry. Shorthand electronic configuration. Write the previous group 0 element and then the rest of electron. Wait, let me bring the periodic table. Not this one, I don't like this one. Which one should I bring? Okay, I'm writing data plate. Yes, this. Look, this is chlorine. So which one is the previous group 0? Previous. Neon? Look, this is chlorine. And the previous group 0 is what? Neon? How many electrons are in the neon? 10. 10. So look, is this equal to neon? Yes, 10. So the shorthand electronic configuration is what? For chlorine, 17. How you'll write? Neon. Neon means 1s2, 2s2, 2p6, and 3s2, 3p5. How many shells? First shell, second shell, third shell, and this is what? Third shell. And how many electrons? 5 into 7 electron. So group number is 7, which we call now what? 17. This is another thing that we are going to do. Now, another element. Suppose we do the configuration of, suppose argon. Argon is what? It's what? Argon. No, not argon. I don't like argon. Sodium. Do it for sodium. We did it for sodium, I think. Can we do it for boron, carbon, nitrogen, oxygen? Yes. Wait. Boron, 5. Carbon, 6. nitrogen 7, oxygen 8, 9, and neon 10. How to do it? Wait a minute. I think just this is sufficient. So 1s, then 2s, and then 2p. Look, it's not good at all. I don't like it. Can I just cut this much? Or neon this way. Okay. Now look. For boron, how many electrons? 5. 1s2, then 2s2, 4. And this is what? 5. So 1s2, 2s2, and 2p how much? 1. 1 unpaired? 6. 1s2, 2s2. There are 2p2. The two electrons are separate because they have space. But how you will write this way? 1s2, 2s2, and 2p2. 2p2. Right? Look. 1s2, 2s2, and 2p2. 1s2, 2s2, and 2p3. 1s2, 2s2, and 2p3. Now, 1s2, 2s2, 2p4 for single and now pair to minimize repulsion. So 1s2, 2s2, 2p4. What about fluorine? 1s2, 2s2, 2p5. 2p5. And neon 10, 1s2, 2s2, and 2p6. 2p6. So 1s2, 2s2, and 2p6. Right? If I do the configuration for potassium, for what? Potassium. Okay. Potassium 19. Potassium 19. One thing. If I want to write the shorthand for boron, so from boron, the previous group 0 is what? Previous group 0 is what? Previous. Helium 1s2. Helium is what? 1s2. So look, instead of this 1s2, what we will write? Helium 2s2 to p1, helium 2s2 to p2, helium 2s2 to p3, helium 2s2 to p4. Do you get? Helium 2:2p5. Now, potassium 19. Potassium 19. 1s2, then 2s2, then 2p6, 3s2, 3p6, 2, 2, 6, 2, and 6. Look, 1s2, 2s2, 2p6, 3s2, 3p6. It is 18 electron. How much? 18. So the 19 electron will go to what? 4s1. 4s1. Now, if you look, first shell, second shell, third shell, and fourth shell. In the first shell, 2, in the second shell, 8, in the third shell, 8, and then 1. So it is in period number 4 and group number 1. Perfect. Look. Period 1, period 2, period 3, period 4, and group 1. Right. And before potassium, which group 0 is there? Before 19, the 18 is what? Argon. So what is the shorthand electronic configuration? This is equal to what? This is equal to argon. This is argon. So what is the shorthand? Potassium is what? Argon. 4s1. So one thing which is very clear, that potassium clear-cut indicate, it is in period number 4, a group number 1, it clear-cut indicate that after 3p electron is going into 4s. After 3p electron are going into 4s. Now, what we are going to do, the next thing is, wait. Can't remove it. So you know what I'm going to do? I'm going to do it again. No way. Wait a minute. Now look. What is the pattern? What is the pattern? What is the energy profile? So what is the lowest energy? Ground state. It's 1s. Then what? 2s. Then what? 2p. And then what? 3s. Then what? 3p. Then what? 4s. But one important point. The 4s and the 3d are very close. The 4s and the 3d are very close. So if I do the configuration of hydrogen, it's Simply what? 1s1. It's what? 1s1, nothing else. I want to write it clear. 1s1. In helium, there are just 2 electrons. So what? 1s2. Helium is what? 1s2. But in lithium, there are 3 electrons. So what is the configuration of lithium? First thing that I'm going to erase is this. Wait, give me some time. I'm going to do the configuration of all these in the periodic table so that you can see the pattern that is obeyed by. In the course, you guys are supposed to know up to krypton 36, but once you do it till krypton 36, it's obvious that you will be able to do it for anyone. But in syllabus, they have written that krypton 36, okay? So come to this. And now, Hashim, you're up to this, it's very fast. Then in scandium till zinc, it's a bit different. I think I have to erase the lower one to accommodate, because my target is krypton 36, and at the end I will do the configuration of all these elements through another method. We do it through periodic table, but that periodic table method is much easier once you do it this way. Like sometimes one method helps the other method. So it's like this. 8. Come. Now there are 3 electrons. So what is the configuration? 3 electrons. 1s2 and then 2s. So 1s2 and 2s1. What about 4? 1s2, 2s2. Definitely. 1s2 and 2s2. 4. What about this? Boron. For boron, there are 5 electrons. 5 electrons. So 1s2, 2s2, and 2p1. In carbon, it becomes 2p2. In nitrogen, it becomes 2p3. And in oxygen, it becomes, okay, wait. When it was 1:2s1, 1 unpaired, paired. 1:2s2, both paired, non-paired. But once for boron, 1:2s2, 2p1, 1 unpaired, 2p2, 2 unpaired, 2p3, 3 unpaired, 2p4. Once it is 2p4, how many unpaired? 2. 2p5, 1 unpaired. 2p6, no unpaired. Like there are many questions which are related to the number of paired and unpaired electrons. So when you do configuration, be careful. This is what? 5. 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, 1s2, 2s2, and 2p6. Right? So if I write the shorthand, so it would be what? It would be, the shorthand would be what? Helium 2s2, 2p1, helium 2s2, 2p. Like instead of 1s2, what you are supposed to write? Helium. Helium. Right? Now, after this, it's what? Sodium 11. So sodium 11. 1s2, 2s2, 2p6. 2, 2, 10, and 3s1. So how you are supposed to write? It's 3s1, and magnesium is 3s2, and after 3s1, and then 3s2, and then 3p1, then 3p2. Do you get? So if I just write here, it's what? 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s2. So this is what? Neon? Neon is what? 10. Neon is what? 10. So what would be the shorthand? Neon 3s1, neon 3s2. This is what? Helium 2s1, helium 2s2. This is what? Neon 3s1, neon 3s2. So what about the other one? Neon 3s2, 3p1. Look, neon 3s2, 3p1. So, but if I write the total thing, it's what? 1s2, 2s2, 2p6, 3s2, 3p1, 1s2, 2s2, 2p6, 3s2, 3p2, 1s2, 2s2, 2p6, 3s2, 3p3, 1s2, 2s2, 2p6, 3s2, 3p4, 1s2, 2s2, 2p6, 3s2, 3p5, and this is 1s2, 2s2, 2p6, 3s2, 3p6. Now, if you look at this in detail, this is period number 1. This is period number 2. This is period number 3. This is period number 4. Agree? This is period number 5. So at the end, it's always 2. At the end, it's always 3. At the end, there must be 4. So if this is 2 is to 2p1, this is what? 3 is to 3p1. The next is what? 2 is 2 2p2, 3 is 2 3p2, 2 is 2 2p3, 3 is 2 3p3, 4 4 5 5. You know, these are called what? P1, P2. They all have this at the valence. P3, P4, P5, and P6. These are called in the periodic table. In the whole periodic table. You know, these are S block element. I'm writing so badly. Wait. Let me do it. There are 2 rows also. So these are called S block. These are called D block element. These are called P block. And these are called F block. You know why? What comes at the end? What is coming? P, 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 P. Now, if this is 2p1, this is 3p1, what should be this? 4p1? 2p2, 3p2, 4p2, 5p2, p3, 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 4, p4, 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 p5, p5, p5. So 1 unpaired, look, p1, p, p1, 1 unpaired, p2, 2 unpaired, p3, 3 unpaired, but p4, 2 unpaired, p5, 1 unpaired, p6, no unpaired. These are p block. They are what? 2s1, 3s1, 2s2, 2s. These are called S block. And there comes D. Right? These are D or D block elements. So what is at the end? It's what? S1, S2, and this is what? P1, P2, P3, P4, P5, and P6. These are called D block. These are called F block. So if there is 2s1, 3s1, there must be what? 4s1, 4s2. Just according to the situation, huh? Following the rules. So this is what? 18, and this is what? 19. 18 is what? 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, and then what? 4 is 1. So in potassium, there would be what? In potassium, at the end, there is what? Clear cut 4s1. And at the end of this, it's what? 4s2. Right? I think this is sufficient for today. This configuration will be my next video. Okay. This we will do in the next class. Okay. I think you understand. If you have any question, you can ask me. Okay. The next we will do in the next class. Okay. Bye. Allah Hafiz.